Hey guys, for today's vlog, we're gonna take you through a pump curve, a centrifugal pump curve specifically, and we're gonna look at a little bit about what they mean. This is something that we commonly use and see when we not just size centrifugal pumps, but also when we communicate to customers what we're quoting them, showing them how they can expect their equipment to perform. We thought that it would be helpful to kind of walk through some of this. It won't be super in depth or super technical, but we'll kind of show you some of the things that we look for when we are reviewing these centrifugal pump curves. Okay, so first let's look at the search criteria, right? So for this application, this customer wanted 141 gallons a minute at about a 60 psi discharge head. The thing to remember for centrifugal pumps is that they're really good to do, medium to high volumes at relatively low pressures. So what does that mean? Medium and high are sort of relative terms. In our world, it typically means between 50 and maybe 250 gallons per minute for flow. And then for pressure, generally we see it anywhere between 10 and maybe 60 or 75 psi. Once we start getting outside of those parameters, we want to review it and scrutinize it a little bit more carefully. You probably want to check with your local distributor, see what they think, rely on their experience. But if it's in that sweet spot, it's a pretty safe assumption that you're going to be in a centrifugal pump. The other thing that we have to have for a centrifugal pump is low viscosity fluids. So we're only using centrifugal pumps in the sanitary space with low viscosity fluids. What does that mean? Generally, that means less than 500 centipoise, though that number tends to creep every time you talk to somebody. So let's start again by looking at our search criteria. So for this application, we have somebody who's pumping 141 gallons per minute at 60 psi of water. Now, where does that 60 psi come from? That's our discharge head. Most of that in most systems is going to be because of either obstruction downline, maybe a filter, some point of loss, but more commonly it's the friction loss, right? So before we kind of get into the sizing exercise, it's important to know what our total discharge head is, and that's going to be the summation of downstream elements, but it's going to be a lot of that friction loss, right? So we'll look at the diameter of the tube, the flow rate that we're going to put through it, the total length, and then we'll come up with a friction loss. Maybe in a future vlog, we'll kind of walk you through a friction loss calculation example. But here it's just important to know that we have about 60 psi of discharge head. Up here to the right, again, this is a pretty standard industry data sheet. We can see that we're pumping water, is specific gravity of 1. The vapor pressure is 0.256 psi. Atmospheric pressure, this is just in Chicago, so it's 14.7 psia. We have 15 feet of head available, so we have plenty to keep the pump from cavitating. Our temperature is 60 degrees, and the viscosity is about 1.1 centipoise. So it's just water. It's very thin stuff. Based on that criteria, we return a search. It says we should use a 2065 pump, right? So a lot of times when you run these search for vendors, they'll offer multiple pumps that you want to look at and consider. In this case, this is a pretty standard duty centrifugal pump. It's for a CIP application, so we wanted something with a robust seal in it. The customer has other 200 series pumps in service, so we went with a very dependable, very reliable pump, the 200 series, the 2065 specifically, with a 2.5-inch impeller, a 2-inch discharge, a 2.5-inch inlet, a 2-inch discharge, and a 6.5-inch impeller. Okay, that 6.5 is actually the full size impeller. As we scroll down here, we're going to see that for our curve, we actually need to have a 5.875-inch impeller. So that means the impeller has been trimmed from 6.5 to 5.875 inches. Okay, we're going to be running a 3600 RPM motor. Again, very common. Centrifugal pump applications are either 3600 RPM or 1750 RPM. And then as we look at our motor data here, it says that we should use a 15 horsepower motor, and we'll walk you through why it says that and whether or not we need to use it. So as we get into the curve, we see a few different lines here. Okay, on the horizontal, we have our flow rate. That's US gallons per minute. On the vertical, we have our head in PSI, right? Sometimes you'll see this in feet. In this case, it's in PSI. That's very important that you want to pay attention to know if this is in feet or in PSI. Okay. So here we follow out our duty point. Again, we have 141 gallons a minute, which is going to be right about here, at 60 psi of head, which is going to be right about here. And as you can see, that falls just below the 5.875-inch curve. If we had used a 6.5-inch impeller, we would follow this out until we hit another impeller curve. So what we'd see actually is if we use a larger impeller, we would get a lot more flow at that 60 psi of head, right? In fact, we'd be getting close to 350 gallons a minute with a 6.5-inch impeller. So that's how you follow it. You follow it all the way out. Okay. So now the next thing you'll see is that it told us we should use a 15 horsepower motor. Well, should we really use that? Let's look at it. The way most of the sizing programs default is it's going to default to a non-overloading size motor, okay? So when we look at this curve here and we follow it all the way out, our dashed lines are going to be our motor horsepower curves, or motor horsepower lines, right? So as we see here, our draw is actually about 7.5 horsepower, right? But if we have any less discharge head, or if our calculation was a little off or a little conservative, we're going to keep running. As we run further out on this curve, what we see is that our energy consumption goes up. So we're going to need more horsepower. And in fact, pretty quickly, we get past 10 horsepower all the way to 15. So the reason why this recommends a 15 horsepower motor is because that is the non-overloading motor size, right? That is the motor size which the entire curve fits under, okay? What's common is people will be more aggressive, right? And there's different reasons they want to be aggressive. One is cost. As you might imagine, a 10 horsepower motor is less expensive than a 15 horsepower motor. And a 7.5 horsepower motor is less expensive than a 10 horsepower motor. Sometimes it's availability. It can also be amperage, right? So we need to look at what the amperage draw of a 15 horsepower motor is and compare that to a 10 horsepower motor and see what sort of utility the customer has in the area. Do they have enough amps to power the pump? When I'm evaluating this, I look at it and I'm probably not going to go with the 15 because we can always increase our discharge head. You can do that with a throttling valve on the discharge, something like that. But I'm also not comfortable being that close to overloading a 7.5. So I'm going to follow it out a little bit further. And for this application, I'd probably put them in a 10 horsepower motor with a 5.875-inch impeller. You know, one of the other things you want to think about too is whether or not a customer is going to be using a VFD. If they are using a VFD, then a lot of times we'll go just all the way to the full impeller size, knowing that they can slow that down, because obviously as you slow down your speed, you're going to get less flow. You're also going to get less discharge head, right? So that's something that we want to review. Just walking through a few other areas on this curve, what you'll see is the best efficiency point for the pump, right? So the best efficiency point of a centrifugal pump, as the name might imply, is the point on the curve where the pump is going to be most energy efficient, right? Generally speaking, we want to be out towards the middle of these curves. We don't want to be all the way to the left, and we don't want to be all the way in the end. We want to try to find a sweet spot, someplace right in here. And in this case, the best efficiency point is at 70.5% of full power, which is right here. So we're out a little ways. I'm comfortable with it. That's fine. If we started going too far left on the curve, okay, we don't want to go too far left or right. As we go too far right, we increase our motor draw and we run the risk of kicking out the motor. As we go too far left, we run the risk of cavitation, okay? So one thing we'll see a lot is, especially in applications that are higher pressure and lower flow, you might think like a homogenizer application, a homogenizer feed application where we really like to use a centrifugal pump. If we get past this red line, that's the shutoff point for the curve. Or of the pump. That's where the pump is going to deadhead and basically you're not going to get any flow out of it. We see a lot of cavitation there, right? And that's when the pump casing gets really hot, the fluid starts to boil, and if you're feeding a homogenizer, that's going to create a lot of problems, okay, from an inlet suction standpoint. So we always want to make sure we're getting out to the right on the curve, because if you go too far left, you start getting into some trouble. Down here at the bottom, we can see that this is just our net positive suction head required. So that's how much, in line with the cavitation topic that we just discussed, how much suction head is required to prevent the pump from cavitating. Okay, and then here we can see at the bottom, we can see just performance evaluation at a few different flow rates and a few different speeds, what the efficiency is going to be, and then also what our power consumption is going to be. Okay. So again, here we're going to use a 2065 2.5-inch inlet, 2-inch discharge. Your inlet is always going to be larger than your discharge on a centrifugal pump, just about always. Sometimes I think you might see size on size, 1.5 inch by 1.5 inch, for example. But generally speaking, as a best practice, we want to keep that inlet as large as possible, get as much flow in as we can. And then we'll have a little bit smaller discharge. We're going to use a 5.875-inch impeller because it fits on this curve real nice. It says we choose a 15 horsepower impeller, but looking at our power draws down here as well as the curves, I'm probably going to be a little more aggressive and go with the 10 horsepower motor, not the 7.5. And we'll put it together for the customer, ship it to them. This will be a great CIP supply pump for them. We'll just use a Type 1 seal, carbon and ceramic seal, and it'll be another happy customer and successful pump installation. So if you ever have any questions about how to review a pump curve or sizing a centrifugal pump, don't hesitate to contact Triplex Sales or any local walk shop pump distributor. We'd be happy to help you in any way we can.